Sai is a scientist. Ark is an artist. While Sai works her mornings making mathematical models of real situations and observing results that will benefit society, Ark doodles in the evenings imagining mathematical reality and sharing his elegant and profound proofs to make himself and his friends happy and inspired. That is why Ark considers the sum 1 plus 2 plus 3 plus 4 and so on and so forth, and attempts to find its sum even though it doesn't exist and simply diverges to infinity. He dislikes that the sum is non-existent, and Ark knows that mathematics is his universe, his imagination, which is why he imagines for his sake and for his pleasure that the sum converges to the number s. The two opposites, Ark and Sai, had collaborated so much when they were young, but now they are no longer friends. As neighbors, they see each other at least twice a day, but not because they want to. That is why, when Sai sees Ark in a problem he is working on, she complains to Ark for never taking mathematics seriously, and wishes that he could use mathematics more as a tool for science and as a tool to benefit society, instead of using it for the sake of doing mathematics and the sake of imagining numbers. But Sai is empathetic. She appreciates that Ark attempts to inspire his friends through his proofs inside his so-called imaginative jungle. She believes that Ark has a kind heart, but not a logical head. Sai leaves, and Ark continues to work on a problem. The evening passes, and Ark finds his result. He first took -4 times the sum, and when he arranges the product in such a way, he discovered that by taking the difference between those sums, s minus 4s, and by taking each sum from each column, he reaches an easier sum to work with, the alternating original sum, 1 minus 2 plus 3 minus 4, and so on and so forth. He knows that this sum shouldn't exist either, but he imagines that it does and denotes it by x. But then he took a copy of x and arranged the terms again, and he found that by doing so and adding the sums from each column, he obtains 2 times that sum, which equals an even easier sum, 1 minus 1 plus 1 minus 1, and so on and so forth. He knows that this sum too shouldn't exist, but he imagines that it does and denotes it by y. This time, he can't find a way to make the sum into a simpler one, but he found a way to manipulate the sum into itself. He takes 1 minus the sum, which equals 1 minus y. But when this minus sign distributes itself, it switches every sign of the sum, making 1 minus the sum equal to 1 minus 1 plus 1 minus 1, and so on and so forth. In other words, the sum itself. Therefore, 1 equals 2 times y, and so y equals 1/2. But 2 times the alternating sum x is equal to y, so x is equal to 1/4. And s minus 4s is -3s, and that is equal to x that is equal to 1/4, so that the final sum s is equal to -1/12. Sai wakes and sees Ark's result. She takes time to process the numbers, the 1/2, the 1/4, and the -1/12. The results are surprising, but that surprise is unwelcome and transformed into her usual complaint. Sai believes that Ark has the proper idea, the proper heart, and the proper curiosity. But Sai believes that the idea in practice is impractical to society. Ark is completely satisfied with his results, but a part of his kind heart subconsciously resonates with Sai's complaint. He was prepared for a mind-blowing result. He imagined that a sum to the infinite converges, and then found a negative number from that imaginative assumption. But deep down, his fundamental self is ambivalent and hesitant. Ark is a lover of numbers, a numberphile, but he's also a lover of logic, a logophile. He can't accept that there is no intuitive way, no visualization that makes even the assumption that a sum to the infinite converges seem reasonable. But Sai leaves Ark's thoughts and carries on with her business. Her business has found recently that society needs a better understanding of objects in freefall, that is, objects that have no forces applied to them aside from gravity. She has been running experiments and has found some patterns. After taking data points and analyzing them, she finds that the perfect function that models the situation is one called the quadratic, a function with a quadratic term, a linear term, and a constant term, with coefficients a, b, and c. She knows that there is only one configuration of a, b, and c that perfectly models the data, To find them, Psi converts the data into how a model would produce it in the first place, which gives her free unknowns with 3 or more linear equations, something Psi knows how to solve. B and C must equal 0, and A must equal negative 4.9. In other words, Psi can calculate how long an object free falls to the ground just by setting the equation equal to the y value she desires to see the object fall. Conversely, just by setting the input variable t in her quadratic equation, she can find how much the object falls by finding the output of the function. She is pleased by this and generalizes it. Instead of dropping the object from some height, she thinks, the object can first be released by some hand that throws it, some initial velocity. Because the initial velocity is something that applies force only once, Psi knows that she only needs to add a linear term to account for the initial velocity. When Psi subtracts the function of t, and treats it as the constant term of the quadratic, c, she is ultimately left with a complete quadratic with 3 constants. This is because Psi knows that when an object is released, an engineer would already know the desired distance f of t, and preferably the initial velocity v as well. The engineer would surely be more interested in the time it takes for an object to reach the desired distance in the first place. Psi now has 2 choices. One, to solve for t in terms of the 2 arbitrary constants and negative 4.9. Or 2, to generalize further and solve for every quadratic equation with the more common variable x and the general coefficients, ax squared plus bx plus c equals 0 in terms of a, b, and c, because then she will be able to reference the solution for any situation where a variable depends on another in terms of a quadratic, linear, and constant term. So, Psi strategizes. She is treating the problem like a science experiment, but with no hypothesis, just a bunch of testing and pattern inspection. She can set 3 constants, a, b, and c, all equal to some value, solve for x by experimentation, and continue the process until the values of x reveal a pattern dependent on a, b, and c. However, she has learned from past experiences that creating a frame and a problem and cracking a special and easier case first is the path to take in simplifiable problems. Psi easily sees the condition that can be eased into an inner frame, the 3 coefficients, a, b, and c. If she sets one to 0, then it is as if the constant didn't exist, leaving her with only 2 left to deal with. Setting a equal to 0 only leaves her with the linear equation, which is already known to Psi to have the solution x equal to negative c over b. To involve the quadratic, she sets a to a, c to c, but b to 0, so that she only has 2 constants to deal with. This case turns out to be easy, and she doesn't need to infer solutions yet. Isolate the x, leaving negative c over a, and take the square root on both sides. She is careful and fully aware that when one takes square root, one needs to separate the solution into 2 cases, positive and negative. No matter the sign of it, a number squared is positive, so that the square root of a positive must be positive and negative. Psi uses the mathematical shorthand, plus or minus symbol, which condenses the idea into one expression of the 2 cases. That is why, when Psi takes the square root of the equation, she uses the symbol to indicate that there are 2 solutions to the quadratic, plus or minus the square root of negative c over a. By plugging the result back into the original equation, she verifies that this derivation is correct and sound. She is not enchanted by this result, because it is one that anyone could have reached, but moves to the case where c equals 0, while a equals a and b equals b. Psi knows that there must be 2 solutions, since this is like the last problem, which had 2, but with a linear term instead of a constant one. It does not take long to find that one solution must always be 0, the first number that comes to mind. The other solution is not so obvious, so Psi begins the tests. She first sets a to 1 and tests out different values of b. With b equal to 1, she finds that x equals negative 1. With b equal to 2, she finds that x equals negative 2. And with b equal to 3, she finds that x equals negative 3. The pattern seems to continue forever, so she then sets a to 2. Then, with b equal to 1, When Psi attempts x equaling -1, the guess is 1 off. But the issue is resolved when Psi changes it to -1/2, half the value. With b equal to 2, Psi tries half the expected value again, which would be -2/2. And it works! The pattern seems to continue for every selection of b. X is equal to the expected divided by 2, or in other words, -b divided by 2. The denominator for a equaling 2 is 2, and the denominator for a equaling 1 is 1. Therefore, Psi reasons, the solution of the equation must be 0 and -b/a. This result is slightly more satisfactory than the other since Psi had to work harder to obtain it. But those two solutions were the two inner frames, and she desires the true general formula that explains it all. She is aware that the two special formulas must have a place in the general formula somewhere. She doesn't immediately come up with ideas, aside from repeating the same process of testing and pattern seeking that she just used. Psi would do anything to obtain a result if it is to benefit society. She believes that results can be beautiful if they test the past of simplicity in terms of length, but complexity in terms of the ideas that the result conveys. Psi loves mathematics because it is always black or white. Numbers are always right or wrong, but a scientific theory is immediately disproved as soon as one counterexample is found. Mathematics is useless on its own, but science applies mathematical reasoning, which makes it unreasonably effective. The small, ambivalent, and hesitant voice that disagreed in her subconscious didn't leave without making a mark. If all she cared about were the results, then she may have without hesitation repeated the same process of testing and pattern seeking in the general case. A logical voice advised that isn't efficient, but a faint emotional voice expressed that is ugly. Psi listens to her logical voice and concentrates on finding another game plan. She scribbles her given info, the two special cases, the quadratic equation, and the number of solutions to the equation. When she tries to implement her two formulas and create a general formula, she still doesn't conceive of ideas, but she thinks that her idea may be easier to think about if the two special formulas had similar features. She sees the plus or minus and attempts to scribble it on the other formula. And by setting the midpoint of 0 and -b/a, and by taking the distance from the midpoint to the two values, the plus or minus symbol is implemented without problems, because the midpoint plus or minus the distance is the same thing as the 2 points themselves. It doesn't seem like progress, but she continues, now attempting to scribble the square root in the same formula, but only after the plus or minus symbol copying the other formula. Now there is one particular characteristic that is universal among the two. They both contain a as their denominator. So Psi decides to leave the denominator on the bottom equal by multiplying a value on both the numerator and the denominator that changes the denominator to be equivalent, so that Psi can then take the square root out to make every denominator of every equation equivalent. When the two finally resemble as much as possible, it seems more plausible to combine the two now. Seeing that the midpoint -b/2a is only in one formula, and seeing that in the other the value inside the square root is different, Psi conceives that the two can be combined by setting the midpoint and incorporating the other formula within the square root. And Psi is happy with her complete result. Whenever she has a quadratic, ax squared plus bx plus c, and that quadratic equals 0, then the solution to the equation is -b plus or minus the square root of b squared minus 4ac, all over 2a. The day begins to set down, and Ark begins to doodle on his paper. When met with Psi's process, Ark got partially bored by the practical applications, but certainly interested in the idea of pattern inspection and in the idea of combining two special cases, although he wishes the ideas were presented more rigorously and elegantly. Psi's interaction with quadratics inspires Ark to think about squares and ideas that quadratics connote. He is aware of the theorem which states that the square of the length and width of a right triangle is equal to the square of the hypotenuse, but has never found a proof of it. He predicts that a doodle picture involving a square, the shape that he is studying in the first place, can prove the conjecture, so he first draws one in the middle. There must also be triangles in the picture, so he attempts to inscribe some. A diagonal in the middle creates 2, but his driving intuition senses that this probably isn't the right way to go. Maybe, his driving intuition conjectures, he can create a square inside the square, to use a relation between the inner square and the outer square. He also creates an inner frame by making the two sides of the 4 triangles equal, so that the inner square takes exactly half the space of the bigger square. If a triangle has a unit side length, then he needs to prove that the hypotenuse must be root 2 long, since that's what the theorem would tell him if it were true. The big square takes an area of 4, and the inner square takes an area half of 4. That is why Arc finds, miraculously, that the side length of the hypotenuse must be root 2 long. To Arc, this proof is elegant in the order of magnitude of 3.1, 1.3 bigger than Psi's derivation of her quadratic formula. This is because he understands the fundamental argument of algebra, that when a result is proved, the same argument in the proof applies to any structure that the argument can attack. His argument never relies on the oneness of the triangle and the fourness of the square. It relies on the symmetry of the 4 triangles and the fact that the inner square takes up half of the space. Thus, for any triangle with equal length and width, the square of both side lengths must equal the square of the hypotenuse. Not only that, but one of the fundamental ideas of mathematics itself applies, that when a result is proved for every structure that the argument applies in, the structure and argument can be expanded, using more flexible concrete and fewer conditions, and more paint-coated arguments and fewer unnecessary steps. When measured, the flexed area is the side length of a plus b squared, but the smaller area is not necessarily half of that. He needs to subtract the areas of the triangles, which is seen as a times b over 2, 4 times. But this is where the argument needs more paint, because although the side length of the smaller square would be the length of the hypotenuse, the expression is ugly and impractical. He attempts to nest a similar argument by scribbling another square inside. Because its side length is a minus b, the now trapped square must have an area of a minus b squared. And because 4 rectangles trap it, Arc argues that a minus b squared plus 4ab equals a plus b squared. He can't make much progress further than this, so he considers another strategy. Just rearrange the puzzle to make shapes that he knows how to take the area of. 15 minutes of puzzle play pass, and Arc does not find the proof of the expansion of 2 measurements. He finds the proof of 4. Although he already knows the expansion of a times a plus b and a times a minus b, he is still charmed, since the proof shows that the expansion has profound connections with the theorem he started with. His doodled picture consists of 2 rectangles and 4 triangles. Arc knows that the right side of the square must have an area of a times a plus b by its length and width. But if it is broken down, it is shown to equal the sum of 3 rectangles, in other words, a times a minus b plus 2ab. But he can also frame the area as the sum of the triangles and a trapezoid. This trapezoid has an area of its average height times its width, which simplifies to a squared. Combining everything, a times a plus b is proved to equal a squared plus ab, and a times a minus b is proved to equal a squared minus ab. The entire square, a plus b squared, is equal to b times b plus a times a plus b, and b times b plus a simplifies to b squared plus ba, since the argument of the theorem does not rely on the fact that the variable has the letter a or b. So a plus b squared is equal to a squared plus b squared plus 2ab, and a minus b squared is equal to a squared plus b squared minus 2ab. And most importantly and elegantly, the theorem that the square of the length plus the square of the width is equal to the square of the hypotenuse is proved. As a meditation on his results, Ark notices that the expansions of the areas have interesting applications. A variable can be numbered in the same way that the theorem's argument applies when a letter name is changed, and the expression changes exactly as he would expect, except that the transformed expression looks like the equations Psi was working with. Ark knows that the inverse process of expanding is factoring, and he conjectures that factoring could be a strategy to solve special cases of quadratics. He is not necessarily interested in the results, he is interested in the process. He wants to find more elegant and interesting ways to study his structures. But it is getting very late for Ark, so he finds one final illustration of the factorization of the difference of squares. He takes a square of sine length a, cuts a rectangle of width b, and rearranges the picture. He then takes away a square with sine length b, so that he is left with a rectangle with lengths a plus b and a minus b, and so that this rectangle has an area that equates to a squared take b squared. This is elegant, but Ark knows that this expansion can be carried out manually by the distributive property. Ark admits that there is cuteness in that simplicity, but only in the order of magnitude of 1.9. There is something so much more elegant about finding a novel visual argument for these theorems. Although mathematics is black and white, to Ark, it is how he paints the black and white that matters. Some days, Ark prefers to splash the paint bucket, and on others, he creates hidden patterns and meanings symbolized by the black and white. Ark believes that if mathematics is black and white, then it is a balanced form of sculpture, a complex form of printmaking, and an expressive form of calligraphy. He wants his friends to realize this fact so much, but they don't listen for some reason. When Psi wakes up, she realizes, through her dreaming subconscious, that not only are quadratics useful, but that the plotted shapes made by the quadratics are useful as well. This shape, called the parabola, is symmetric in curves, just enough so that a projectile's trajectory follows the shape, in the same way that the y-value of a falling object is calculated using quadratic relations. Psi sees symmetric curves every day, including ridges, antennas, and water fountains, and after testing, the parabola created by the quadratic function turns out to be a perfect model for their shapes. She characterizes these parabolas by their extreme value, the vertex, and how fast the curve curves. After testing some examples, Psi finds a pattern. With a standard form ax squared plus bx plus c, the x value of the vertex is always at negative b over 2a. She recognizes this in her quadratic formula, and it clicks. The vertex must be the midpoint of the symmetric shape, between the two solutions, or equivalently, the x-coordinates, when the y-coordinates are 0, which is why negative b over 2a is the term before the plus or minus symbol in the first place. And with the x-coordinate of the vertex, the y-coordinate of the vertex is easy. Just plug in the x-coordinate of that vertex in the original equation to see what it pairs to. On her other hand, Psi may start with the simplest case and utilize function transformations to find different quadratics, while quickly obtaining information about the location of the vertex and how fast the curve curves. If the vertex is at some point, h, k, and the curve curves at the same rate as the original parent function, then Psi is happy to be able to apply what she has recently uncovered, that a horizontal shift by h corresponds to subtracting the input by h, and that a vertical shift by k corresponds to adding the output by k. As for the rate at which the curve curves, she does not need to both horizontally and vertically stretch the function. She only needs the vertical stretch, because horizontally stretching the function has the same effect overall with a tweak in the other stretch factor, which means that the two stretches can be represented as a single number in the vertical stretch factor. Psi knows that the coefficient of x squared in the standard form is denoted a, and uses the same letter here, since when this new form is expanded, the two must be equal. Psi hypothesizes that this new form that she created, which she calls the vertex form, can always be represented by some standard form expression. It doesn't take long to verify this, since now that she has got the vertex form into the standard form, she just has to compare the differences between starting from vertex form and converting to standard, and starting from standard form itself. By comparing the coefficients, she reasons that negative 2ah must equal b, and that AH squared plus K equals C. Psi notices that this proves that H, defined to be the x-coordinate of the vertex, is negative b over 2a, the assumed x-coordinate of the vertex. She thinks this is in some ways neat, but moves on. For some given a, b, and c in the standard form, both equations have solutions, and for some given a, h, and k in the vertex form, both equations have solutions. In other words, every standard form is some vertex form, and every vertex form is some standard form. To Psi, this is a huge result, since this now means that she is able to model parabolas using vertex form instead of standard form. Once given a vertex, h, k, she only needs to know how fast the parabola curves, a, to find a perfect model. To find a, Psi needs just another point in the parabola. She reconsiders this for a second, in the case that the second point does not lead to a unique vertex form expression, but reassures herself in a second by sketching a proof. As a increases, the curve goes up. As a decreases, the curve goes down. And as the curve oscillates, only one unique constant a makes the parabola pass through the second point. Solving for a just by equations is not too difficult. She has to use the information and transform that information into equations. If she has the vertex, h, k, and another point, then the relation is given by the desired function. Since every constant besides a is given, a must exist, and must only have one unique solution, as more evidence that a second point leads to a unique vertex form. She hears that she likes the pictures more than the equations, according to the faint voice of her deep heart. But the equations are more useful because they prove the uniqueness of a and additionally find the exact value of a. The voice sleeps once again and Psi moves on. Glancing at her window, she sees another useful and ubiquitous shape, the circle. She already knows the equation for it. R squared equals x squared plus y squared, where r is the radius of the circle, a fixed constant or parameter. As her eyes cross the equation, and cross back to the equation for the parabola, she interprets the parallel structure among the lines, the parallel structure of the square. From the time she first found an unexpected correlation between two completely different real-life phenomena, she has always loved to generalize. To generalize is to invite other objects to the festival, objects that are found to share expected or unexpected characteristics. The circle is a quadratic, but a quadratic with two variables. The circle is not a function, it is an equation with a set of solutions that when plotted creates a shape. It can be shifted horizontally and vertically, and when expanded, linear terms appear. But the circle is also a special case of the more general shape of the ellipse. Psi is aware that ellipses are also useful shapes. She sees them every day when she looks at circles, not directly overhead but from an angle. One application she is especially charmed by is the shape created by the orbit of a planet around the sun. The ellipse is also a quadratic with two variables, x and y. It is again not a function, just an equation with a set of solutions that when plotted creates a shape. And again, when expanded, linear terms appear. That is why Psi defines the general quadratic as two square variables, two linear variables, and a constant, all with some coefficient, and all equaling 0 so that she has an equation with a set of solutions that satisfy it, and not a function. Every possible ellipse, circle, and parabola is represented diversely in this general form. Psi loves to generalize, because generalizations, always, without exceptions, lead to discoveries. If three shapes share a trait, then there so often is a new undiscovered shape that also shares this trait. And this undiscovered shape is unearthed by Psi when she makes one of the coefficients of the quadratics negative, as opposed to both being positive or negative. When the equation is plotted, she is astonished, because she recognizes this shape called the hyperbola. This shape that can be cut in half and taken to the third dimension to create a potato chip. But on her second thought, it is not nearly as astonishing when she recalls that the hyperbola is a shape defined as a special set of points, similar to the ellipse and circle. A circle is the set of points where the distance from a focal point, the center, is always equal. An ellipse is the set of points where the sum of the distance from two focal points is equal, where the sum of the length of the two connecting lines is always equal. Similarly, the hyperbola is defined as the set of points where the difference and the length of the two connecting lines is always equal. But if these shapes have alternative set distance definitions, then the parabola must very, very likely have a set distance definition as well. That is why Sai loves generalizations, because they always arouse something unexpected. She knows that finding this set distance definition for the parabola must lead to applications, in the same way that the set distance definitions for the other shapes do. Finding this set distance definition for the parabola may not be sufficient, however, since Sai needs to find the deepest and most fundamental connection between the shapes to truly understand why her generalization works and why these shapes can all be defined with set distance definitions. Although these discoveries should supposedly be useful, perhaps she is doing this because she loves to generalize, and because she loves the process of discovery. She embarks on her journey, concealed in her wonderful world, not to be opened again until she finds her result. The day begins to set down, and Ark returns to his sketchbook. Again, he enjoys some of the ideas that Sai made, especially that of generalizing the quadratic, but was not enchanted by the applications. Ark hopes that Sai can discover increasingly more beauty inside their mathematical reality as they progress. From his progress in the discovery of special products, including a plus b squared and the difference of squares, he reaffirms he wants to find it, his own elegant quadratic formula, his own method to solve his quadratics, his beautiful proof that could, perhaps, sublime Sai to see what it means to art. Sleeping in the middle of the day, his subconscious dreamt potential ideas to implement. He previously discovered that the expansion of the special products could be inverted or factored. His subconscious took about 60 minutes to osmosis the problem and plant a stylish answer. Ark first transfers the original area of the problem, x squared plus 2x plus 1, into an actual area similar to his previous proofs of the previous day. Then, if factoring is about finding the lengths of a rectangle that, when taking the area off, equals the original area, and if this area must equate to 0, the only time this equation holds is when a side length is equal to 0. That is why, his sleeping intuition reasoned, the solution to the equation, when factored, is the values that turn the side length to 0, and that is why, as long as the repeated solutions are counted, there must always be two solutions to a quadratic, because there are two sides in a factored rectangle, two solutions that turn those sides into side length 0. Already Ark has approached several quadratics and attacked them. Any quadratic that follows the pattern of a special product is solved first by factoring and then finding those two special values that turn the factor to 0. And because they turn the factor to 0, the equation is satisfied, and the values are the solutions for x. Ark, a creator of patterns, now extends the special products to find more possible cases. Instead of creating perfect and complete squares, Ark will be more inclusive were he to consider the broader rectangle class, and his solution method of finding values that turn a side into 0 would still work completely. In that case, the two numbers that factor will be different, and he would have two distinct solutions instead of two repeated. Ark acknowledges that this factorization seems difficult, and acknowledges that if he had some different personality, he could have gotten stuck on the problem for weeks. But because Ark is an artist, and because he has found, by his luck and creativity, the geometric visualization needed, the problem ends almost easily for him. He needs two ideas, manipulation and backward motion. Even if the problem begins with an ax squared plus bx plus c, the equation can be manipulated by dividing a. This changes the equation but still keeps all the information about the solutions so that the coefficient a is only there for cosmetic purposes. So, Ark is able to, for the sake of convenience, assume that the initial quadratic he starts with is a quadratic with a equal to 1, so that the names are less convoluted. Then, when he begins the problem, as always, he represents the problem in terms of the areas of rectangles. But now, working with backward motion, he starts with the result, the desired rectangle. By his previous experiences and the fact that the coefficient a is set equal to 1, he knows that this rectangle would have the length and width of some x plus p and some x plus q, p and q being the perfect two small values that add with the x to constitute the rectangle. By adding up all the small puzzle pieces, this rectangle is found to have the area of x squared plus px plus qx plus pq. With the distributive property, or synonymously, with one of the special rectangles he found earlier, he can reason that qx plus px is just equal to q plus p times x. But this is almost like the initial condition he begins with, except how silence p and q contribute to the area instead of coefficients b and c. In other words, if arc assumes that a factorization exists, and that factorization leads to psi length x plus p and psi length x plus q, then b must equal p plus q, and c must equal p times q. He just needs to find these factors, and they are found with the strategy of finding factors that make p times q, and checking if those factors, p and q, add up to b. This step of finding the perfect pair is a very unique strategy, because unlike almost all of the problems in algebra that ARC has dealt with, the solution to this problem depends on the actual numbers themselves, and ARC needs to make the arguments that consider how b and c are some numbers with unique factorizations. Once the perfect match of p and q are found, the solutions of the quadratic are the values that turn the sign length to 0, in other words, negative p and negative q. This strategy, ARC finds, even works for negative numbers, although ARC does not like them as much because they aren't as easily represented as an area of rectangles. Theoretically, his result applies to any quadratic that satisfies the assumption of this proof, that there exist two factors with side lengths x plus p and x plus q that equate to the sides of the quadratic. But ARC sees that in a more practical sense, it is not complete. Finding the factors themselves can be very difficult, even with small numbers. He said that he can always divide by a at the beginning, but if the coefficient b or c is not divisible by a, then when he divides by a he obtains fractions, and he is completely aware that finding factors that add or multiply up to a fraction is tedious and time-consuming. That is why he tries to generalize his result, by still including a in his quadratic, and h and k as products of x in his factors so that they multiply up to a. Through his visualization, he is able to expand the area elegantly, and through his same previous method of comparing the coefficients, he discovers that h times k equals a, q times h plus p times q equals b, and p times q equals c, so that the value of h, k, p, and q can be found similarly to the simpler case by trial and error. Instead of the solutions just being negative p and negative q, the solutions would be negative p over h and negative q over k, because those are what make the side lengths equate to 0. Like the previous result, this theoretically works for any quadratic with a factor of both sides. But this, to ARC, is not much of a step in the right direction, and is more like a bandage to the few additional quadratics that are now evaded because of this discovery. Although he now attacks a few fractional solutions, he is aware that the solutions can be square roots, as shown by psi. And the coefficients themselves can be anything they want to be if ARC is willing to let them be free. Overall, ARC weights his process so far with elegance in the order of magnitude of 2.2. It is an elegant idea to go from the special square to the general rectangle, and to use the techniques of manipulation and backward motion, but this generalization is as far as it gets. The ideas themselves to ARC are beautiful, but the ideas in practice do not turn as practical as ARC would want. This process shows ARC that factoring is powerful, but not nearly enough to solve every quadratic. For that, he still needs a formula, or some process that will flawlessly be able to solve every quadratic. He needs to give up on factoring because sometimes it is impossible to find side lengths that perfectly represent the area of a quadratic. ARC is forced to lift his pen because his subconscious and conscious have run out of ideas. He is frustrated because even the more general rectangles could not be inclusive of all his quadratics, and he can't envision any shape more general than a rectangle, these imperfect and incomplete shapes. In reality, his mind has known this whole time, keeping it locked like an infant with their siblings' toys. It is right there, right in his neighborhood. He utilized backward motion by assuming that the rectangles represent the sides perfectly, but he knows, beyond that there is already an answer to the quadratic, indicating that he can utilize backward motion with the actual true and perfect result. ARC is reluctant to apply a scientific discovery, but when he recalls the square root, it plants him with interest and hope. That square root shows that at some point, in some elegant proof of some perfect book of proofs, ARC takes the side length of a square, this perfect square that could somehow represent the area of his quadratics. But the other terms, including the midpoint term, show that the square in this perfect proof must not be the only shape Arc needs to consider. Arc is imaginative here, though, because he understands for the first time what this must mean. Mathematics, to Arc, is his jungle, his imagination, which is why, when he imagines that the quadratic is represented as a square, all he needs to do is just make sure that when he takes the square root on both sides, that one side captures the unknown value completely, so that the other side is left over with nothing but constants, and so that an unknown side length can equal a constant side length. Instead of turning the full quadratic into a rectangle of uneven sides, Arc creates a perfect square encapsulating not only the square term but the linear term by cutting it into half and attaching it to the sides. And to complete the square, Arc just needs a smaller square with a side length of half of the side length of the linear term and put it on the corner. This value was not there at the beginning, so it should go on the other side as well. When the initial constant moves to the other side, it creates another constant that has some side length. And when the side length of both sides is taken, the side length of the known constant area can be positive or negative, because the negative value squared is equal to the positive value squared, although it is not possible to be visualized. That is the square completion argument. And that argument is strong enough to have no dependence on the property of a certain subset of numbers, and strong enough to get from a completely unknown quadratic to a completely solved solution. Arc now applies the fundamental argument of algebra, because every argument used so far has relied on the fact that he has real numbers and nothing more than that. The only thing he can't do is simplify some numbers if he has to take a fraction or a square. But that is the one thing he does. He simplifies his b over 2 term. Arc does not like that the final result is so complicated, and realizes that the so-called midpoint of the quadratic, negative b over 2a, is just minus b over 2 if a is equal to 1. So Arc replaces b over 2 with the negative of the midpoint, and b over 2 squared with the square of the midpoint. Arc, with his heterochromatic eyes, explains that this is why the solution of his quadratics is m plus or minus the square root of n squared minus c. And this is the perfect proof that even explains why his formula is the root of size formula, because when Arc starts without the simpler case, but starts with the standard case, and divides his standard quadratic by a, b turns to b over a, c turns to c over a, and when those replace b and c, they transform Arc's formula into size formula. Two weeks later, on the 17th night, Sai wakes up and, along with her, wakes Arc from his nap. Within those 2 weeks, Arc and Sai, they had experienced creative insights and frustrations, making discoveries, and finally, the two had gotten closer and begun to converse more friendly, making them more open to interpreting ideas from each other. On the one hand, after finding his argument of completing a square, Arc challenged himself by imagining a third dimension, a cube, a structure connoting a cubic formula. On the other hand, Sai similarly took the idea of the third dimension in her process of generalizing the quadratics. Instead of creating cubes, she created three-dimensional shapes from two-dimensional relations. In the same way that a two-dimensional graph represents every one-dimensional point of a satisfied relation in a single picture, she sought to discover some perfect three-dimensional shape that represents every two-dimensional general quadratic. She had also promised to find a set distance definition for the parabola, analogous to those of the hyperbola, circle, and ellipse, but that did not take longer than 2 mornings to find. She was already aware of the formula to find the distance between 2 points, recently proved to be true by Arc's theorem that the square of the two side lengths of a rectangle equates to the square of the hypotenuse, implying that the square of the distance between 2 points equates to the square of the distance in x plus the square of the distance in y. By that point, Sai was thankful for Arc's proof and thought that it was neat because the proof had been proven to be useful. And the set of points that satisfied the set distance definitions must also then satisfy the distance formulas, with one input as the focal point, the other point as the desired point. It meant that her combination of distance formulas must simplify into a single quadratic term and linear or constant terms. Not two stationary focal points, but a stationary and a moving focal point, Psi found, ensures that one of the distances has no change in x, so that x and x cancel out to leave a single variable. Her final result had the proposition that a parabola is a set of points such that the distance from a focal point and the distance from the straight focal line is always equal. Thus, every general quadratic, circle, ellipse, hyperbola, and parabola, can be stated as some collection of points following a rule imposed by distance functions. Finding this result, Psi wanted to take her generalization further and truly find a profound connection underlying her shapes. Psi knew the most obvious route into the third dimension would be to find some shape that depicts some quadratic at every z value. But any shape that could somehow achieve this feat would look completely messy, and messy results do not yield benefits. That is why Psi generalizes the idea of taking a z value. Since to take a z value is to take the intersection between a flat plane and the desired three-dimensional shape, she can instead take the intersection of any slanted plane and the desired shape. And that is why Psi is awake on the 17th night, because she has just found her shape, and because that shape is so simple, so useful, and so beautiful. And that shape is a cone. On the other hand, Arc was struggling to find a working strategy in his journey to the cubic formula. Taking the square completion argument into the third dimension, he now has the cube completion argument. He starts with the equation x cubed plus bx squared plus cx plus d, without the leading coefficient a, since he can just always divide the whole equation without changing information about the roots. Like his process of completing a square, his strategy would be to begin with a cube of length x, and extend the length, width, and height to some x plus y. And like his square completion argument, this extended part would equal the x terms after the cubic. In other words, the quadratic and the linear terms, bx squared plus cx. Finally, he would complete the cube with a y cubed. The cube has a volume of x cubed, plus x squared y 3 times, plus xy squared 3 times, plus y cubed. The extended part, the part that is asked to equal bx squared plus cx, is then equal to 3 times of x squared y plus 3 times of xy squared. He can rearrange those pieces into a rectangular prism with length 3y, width x plus y, and height x, another way of saying that he can factor the expression into 3y times x plus y by simply taking the common factor one by one. Additionally, the other side also has a common factor of x in its terms that factors out as well to x times bx plus c. Arc simplifies, and the equation turns into bx plus c over 3y equaling x plus y, the desired solution, so that Arc just needs to find b, c, and y to solve for it. Now, going back, if he utilizes an equation analogous to the equation in his square completion argument, he would have an incomplete cube without y cubed, plus the constant term, that would all equal 0, so that by completing the cube he has a cube equaling y cubed minus d, a cube that has a psi length of x plus y. He takes the cube's psi length, but then gets stuck because solving the equation would solve it in terms of y and d, where y is a constant that Arc did not begin with. Arc needs to solve x in terms of b, c, and d, so Arc tries to substitute the expression he found for x plus y. He cubes the equation, takes out the y cubed, and sends it to the other side. But then he is left with a variable to the 6th power, with 2 variables up to the 3rd power instead of 1. This is where he made the unfortunate realization: completing the cube is not strong enough to solve the cubic equation. He was reminded of how he proved the theorem of his triangle's relationship with squares. The argument used for the inner frame was flexed and applied again to the outer case. It by itself truly was strong enough to prove the theorem, because the special product he found, a plus b squared, was just something that came up in the process of his proof. However, in this case, the process of completing a square is not sufficient to prove the result, even with additional medical aid. The process only made the situation worse by introducing additional variables and turning 1 into the 6th power. Arc needs some stunning, beautiful argument, and he needs to apply it at the beginning of the proof, and not where he got to from the cube completion argument. He is creatively frustrated, but not sad. Ark is an artist, and all artists struggle, but creatively, and Ark has learned to embrace the struggle. And that is why Ark is awake on the 17th night, because he has just found that argument, that elegant argument used in the first stanza of his poem, the lead-in to his desired conclusion, and this poem can now finally be finished with his failed cube completion argument. Ark recalled his theory of the midpoint -b/2a in his quadratic, and he had found that an analogous point exists at an inflection point at -b/3a, or -b/3 because a is set equal to 1. At this point, the cubic switches from curving down to curving up. Over it, he noticed a double reflective symmetry, where a side needs to be reflected both horizontally and vertically to match its counterpart. Ark believed if the quadratic formula included a -b/2a term, then the cubic might as well include a -b/3a term. Ark is a mathematician, or synonymously, an artist. And an artist is not only a detective of patterns, but an author of patterns. He imagines that his inflection point is actually at the x-coordinate of 0, so that the entire function is shifted horizontally to the left by -b/3, which he remembers should mean that -b/3 is added to each instance of the input. The quadratic term, elegantly, but not surprisingly, cancels out to leave a cubic, with only a cubic, linear, and constant term. He has reduced the problem sufficiently enough, so that in his progression to complete the cube, the same coefficient b evaluates to 0, and so that when he rearranges and when the remaining c/3 cubed crosses the equation, his poem ends with a final argument of symmetry. Y times y times y times y times y times y is a square with side length y times y times y. He can extend the length and width using rectangles with side lengths that are half of -d and create an equation, and he can complete the square to solve for the cube of y, and he can solve for the cube of y by taking the side length of the cube. He returns once again to his old relation between the y and the x, but without its bx term, and he solves for the final solution of x in terms of y and c. A cubic is x to the power of 3, meaning that there are 3 solutions to every cubic, in the same way that there are 2 solutions to every quadratic. But if one solution is found, only 2 solutions remain to find, in other words, a quadratic, which is already solved by Ark's quadratic formula. On the other hand, Psi was unsatisfied with her finding of the cone and the fact that it is a perfect model for the circle, ellipse, hyperbola, and parabola. The plane has the equation of z equaling ax plus by, and the cone has the equation of z squared equaling x squared plus y squared. All she needs to do to prove that the cone captures every general quadratic, then, is to take the intersection between the 2 equations by setting them equal to each other. Find that the equation simplifies to some general quadratic, and she is finished just with that. But Psi is a scientist, and to be a scientist means to make discoveries, and those discoveries are there not just for their sole purpose, but to strengthen the ties between fields. What she just did was tie a bridge from the theories of general quadratics to sections of the cone, and she needs to do the same for the theories of set distance definitions and sections of the cone. She needs to prove, starting from the cone and the section, that taking a slice of a cone creates a general quadratic. And of course, she needs a challenge. Taking the intersection between 2 equations is such a simple idea that it does not appeal to her. She needs to find a novel idea, so that is what she attempts. She has 3 cases that she needs to prove, since the case of the circle is obvious and also a special case of the ellipse. She knows already that these shapes are ellipses, hyperbolas, and parabolas, so that the set distance definition also applies, including the focal points that those definitions introduce. In the case of an ellipse, 2 focal points must exist somewhere, and the distance from those points to a point on the ellipse must always be constant, at least according to a proof somewhere in the perfect realm of a book of proofs. Attempts of strategizing are made, and Psi can only think of turning back to the equation of a cone, one idea she has already turned into a proof. But that proof, to Psi, was not very insightful. It was a clumsy idea that applies to almost any situation, one that does not highlight anything special about her symmetric shape. She is drained of energy and moves on to the case of the hyperbola. the hyperbola where she needs to take the difference between the two distances rather than the sum. In the case of the hyperbola, there are some special features in the shape that could prove to be useful. For instance, the fact that the shape is so symmetrical. Maybe, since the shape that contains the hyperbola is a double cone, she can make the argument that a double cone implies some symmetry for the sliced shape. But this idea is not only not sufficient, it is not applicable to the case of the ellipse or the parabola. She shuts her eyes, but not because she needs to imagine, but because she can't imagine. The case of the parabola, with its focal point in line, can't possibly be any better. And she gets ready to sleep, maybe ready to come back to the problem another day. The discoveries that she has made in the past weeks have been truly extraordinary. They are discoveries that invite the path to so many other ideas, and they are discoveries that have inspired her childhood friend into the course of the cubic formula. These discoveries are so profound that those weeks could have been months or even years in the making. But in this adventure of Sai has plunged herself into a sea of logic, a sea of explanations. Those explanations showing that mathematics is a science by itself, a science created from science. Mathematics is the purest form of science. It is the pursuit to explain her realm of mathematical forms, born from the pursuit to explain her universe. And this imaginary realm is a place for everyone to go, and a place for everyone to share, including Ark. Ark had just finished his cubic formula. His sublime proof path leaves him with admiration and awe. But when Ark sees Sai and her progress on something that seems like art to Ark, from the accumulation of the 2 weeks and his elegant proofs, and seeing how Sai has changed over time, he is reminded of their closeness in their childhood. He wants to go to mathematics with a friend. He wants to re-establish his friendship with Sai so that he is able to understand her again, emphasize with her again, and love her again. Ark sees Sai in her struggle to explain the cone slices, steps out of his solitude, and confesses the developed truth. The realm of mathematics and imagination wraps the two lives together, and the phrase, "I miss us," resonated in the middle of the night through the universe of no sound. That is why the two chase further into the night, and that is why they napped together. They take their needed break, and they wake up from their final dream of inspiration, in their most focused and creative flowing state. And they are ready. Given the cone and the slicing plane, they know that some construction must create the two focal points desired. The final result asks for a demonstration that the sum of the distances is always constant. But if the sum is always constant, then the final demonstration has a picture with something that always stays constant. But the set distance definition states that the distance is constant for all points on the ellipse, so that the something that always stays constant must revolve around the ellipse. They immediately see it, the cone. The cone has perfect rotational symmetry, with circles making up every z-value, so that no matter what part outside the cone, the length from a circle to another circle is always constant. They have reduced the problem already. Now they need to find some construction that can locate the focus points, and transform the two distances into the constant line made by the two circles on the cone, two circles that must also be located perfectly by some perfect construction. Symmetry in the cone has saved them, and so they imagine that it will save them again. Many symmetric shapes exist, but by far the most symmetric one is the sphere, the shape that is made by the circles that make the cone. But if this sphere constructs both the focal point and the circle on the cone, then it must be placed at the point where it meets the slicing plane, which constructs a unique point that is a point where the sphere just perfectly touches the slice. But then to construct a unique circle, the sphere must scale to a unique size, and that unique size can be met by making the edge just perfectly meet the cone. They do the same thing for the sphere below. To prove that this truly is the construction that proves that the slice of a cone is an ellipse, they first take the distance between the now generated focal points and a point on the ellipse. They then need to morph those distances, without changing the length, into the constant line that revolves around the cone, covering all points of the ellipse, showing that the distance is always equal to the line no matter what points on the ellipse they take. But the sphere is a completely symmetric shape. The distance from the focal point to the ellipse point is a special distance that just touches the edge of the sphere, and so is the distance from the ellipse point to the circle point. It just touches the edge of the sphere. Therefore, those two lines must have equal length because symmetry. And therefore, the same can be said for the other pair of lines. And that is why slicing a cone creates an ellipse. The same construction can be made for the hyperbola, a sphere that just touches the slicing plane and cone so that lines from the focal point and circle have equal lengths. The distances in the hyperbola are subtracted, but that is somehow perfectly accounted for by the circles. It ultimately works down to the same style of demonstration, so they move on to the parabola, the shape that includes a focal line instead of a focal point. But by locating the approximate location of where the focal line should be, they realize that the focal line should just be the intersection between the slicing plane and the plane that aligns with the sphere's circle. A similar demonstration is therefore also possible with the parabola, and their initial goal is achieved. But they have not extinguished their imagination yet. They are still in their inspired creative state, and still have things left that they can do. So when they look for something else to explore, they see that the cubic formula can be elaborated on further, perhaps by finding a simpler cubic formula like the simpler quadratic formula. But mathematics, to them, is their realm, their imagination, and when that imagination becomes too damp, their swamp muddles by overflowing wisdom. In the case x cubed minus 15x minus 4 equal to 0, the cubic has a clear solution, x equal to 4. When they test their cubic formula with the equation, however, they reach a complete contradiction. After simplifying what the formula should say to be a solution to the equation, an impossible number emerges, an expression involving the square root of a negative number. A square root of a negative number is clearly known not to exist, because if it did, then the square of the number must be negative, and it is known that the square of any positive or negative number is always positive. An expression like such would only exist in a realm filled with illogical messes. But according to the solution of the equation, the contradictory number must equal 4. The divine spirit found a sublime outlet in the wonder of analysis, that amphibian between being and not being, which they call the imaginary root of negative unity. If they do completely exhaust their imagination and accept that the number cannot exist, but also exists as the very concept of being imaginary, then the square root of negative 121 is the square root of 121 times the imaginary, the same as 11 times the imaginary. They are distasted, and their mind breaks down. No possible representation of the quantity is present, other than defining it to be an imaginary. But they still need to take the cube root of negative 2 plus 11 times the imaginary, and they are forced to imagine further. They fantasize that the quality is equal to yet another number, plus another times the imaginary. When they are lucky enough to encounter an imaginary squared term, they are able to simplify it down to the square of the square root of negative 1, the number in the realistic world of negative 1. And when they are unfortunate enough to encounter an imaginary cube term, they are forced to simplify the expression down to some imaginary squared times the imaginary, the same thing as negative 1 times the imaginary. After simplifying, they know that the part in the real world must equal negative 2, and that the part in the imaginary must equal 11. And they finally squeeze out the number, negative 2 as the real part, and the number 1 as the imaginary, so that the cube root of negative 2 plus 11 times the imaginary is equal to negative 2 plus the imaginary. They then trudge to find the value of negative 15 over 3 times negative 2 plus the imaginary, and let it equal yet another number plus another times the imaginary. They go through algebraic manipulations again, replacing the square of the imaginary with negative 1, taking the real part, taking an imaginary part, and finally squeezing out the number 2 plus the imaginary, all in their hallucination that the imaginary would function like a normal number, and that the imaginary can be manipulated like a normal number. But if this hallucination is a real fantasy, then they are able to plug in the value 2 plus the imaginary for the fraction, and miraculously, counterintuitively, and astonishingly, the chimeric imaginary cancels each other out, leaving out the solution to the equation as 4. They recognize the fantasized world that they have created. On one hand, everything has gone to an illogical water of reasoning, and they are thoroughly exhausted. But on their other hand, however, they realize, with their tiniest bits of positive emotion, that the result implies some hidden mystery. If the formula states that the number cannot exist, but then transforms into an imaginary mess, which then simplifies to a regular, elegant number, then that imaginary mess could be, with the ever so slightest chance, a mess of beauty, a mess that is chaotic enough to be able to transform itself into a real number, and back into the imaginary. And the square root of -1 may not be the only imaginary. If the square root of -1 is imagined, then they would think of imagining the cube root, the fourth root, and the fifth root of -1. But as soon as they think of it, they realize that they must be wrong, because the third root of -1 is -1, since the third power of -1 is -1. However, they realize that, on the other hand, if they treat their problem like an equation with a variable equal to the cube root of -1, then they have a cubic with -1 equal to x cubed, so that x cubed plus 1 equals 0. And that means they can factor this expression, since -1 is a solution to the equation, and they know that one divisible factor is x plus 1, since -1, the solution, plus 1, is the value that turns a factor into 0. But this means that there are still two solutions to the problem left to find, and those can be found by first finding what should be left over after taking a multiple away. X cubed plus 1 divided by x plus 1. With the help of long division, it is found to be exactly x squared minus x plus 1, a quadratic that they already know how to solve. And when they use their quadratic formula and find the numbers that turn the factor to 0, in other words, find a solution to the equation, they reach an impossible expression again. Normally, this would mean that their equation only has one solution after all. But they have depleted their imagination already, and figure that they can utilize the same inelegant trick here, except the solution this time does not transform back to a real number. It stays inside the imaginary mess of a realm. If their imaginary unit truly exists, then this implies to them that the cube root of -1 also lies in the imaginary realm that was constructed from a square root and not a cube root. They attempt the same for the fourth root of -1, and they reach a similar result. By letting the solution equal x, they find that x squared equals plus or minus the square root of -1, the imaginary. They let the solution to that equal a number plus a number times the imaginary, and after going through a similar process as they already have, in which they assume that this imaginary realm follows the rules of algebraic manipulation, they find that x equals 4 solutions, all inside the imaginary realm. It is one thing to drain imagination by imagining a number that can't possibly exist, but it is another thing if that number that can't possibly exist can transform back into the real world, if the square root of that number is also in the imaginary realm, and if the third and fourth root of -1 is also in the imaginary realm created by the second roots of -1. In fact, they notice a pattern in taking these roots. The square of the real part plus the square of the imaginary part is always equal to 1, closely resembling Arc's triangle theorem. Everything comes back to 1, the most fundamental constant, and -1, the value that equals the square of the imaginary. They need further analysis and inspection of the constants to discover what truly is happening in this messy realm of the imaginary. The culprit to the mess that has been conceived is -1 squared, the fact that a negative number times a negative number is a positive number, and not a negative number like -1, for a reason that they don't remember why. Multiplication in the negative numbers does not follow its conventional definition. Multiplying a positive number by -1 is not synonymous to taking -1 copies of that positive number, nor is it synonymous to scaling the length of an arrow that represents the number. The negative numbers are another imaginary realm all on its own. They defy the notion that all numbers must always increase or stay constant. When the positive numbers are multiplied by a negative number, the arrow representing the number must change directions and retreat. In the best visualization that captures every number known so far, multiplying by -1 is synonymous to rotating 180 degrees to go to our array. That is why the mathematician defines multiplication by -1 as a change in direction or a rotation of 180 degrees. By rotating 180 degrees twice, they see that the arrow comes in a full revolution back to 1, which is how they explain why -1 times -1 is equal to 1. Because they start with -1, a 180 degree rotation, and add 180 degrees by multiplying -1 to that number, leaving a full revolution that is equal to 1. Multiplying by -1 does nothing to how large the arrow is, and instead changes its direction. However, to see that multiplying by something like -2 would rotate the arrow with the addition of scaling it by 2, because negative 2 is a combination of the operation of rotation and scaling. And this happens from multiplying, not adding or subtracting. Multiplying, the operation that transcends addition, but the operation which exponentiation transcends. Now, instead of taking a single number, they take the entire number line as their input. In other words, they take a transformation. Multiplying by negative 1, the number line does a 180-degree rotation, and multiplying by negative 1 again returns them to where they started. They return back to the roots of negative 1. In the same way that multiplication by negative 1, not 2, but 1, does not change the length of the arrow, the square of the real part plus the square of the imaginary part is always equal to 1, analogous to Ark's theorem of triangles, implying some hidden second dimension. Psi went from the 2-dimensional quadratic to the 3-dimensional cone. Arc went from the 2-dimensional square to the 3-dimensional cube. But those were all achieved by imaginative ideas. Kirby did not achieve this feat by imagination. They achieved it by the awful contradiction that they could not bear, in which they were forced to fantasize some imaginary mess of a realm. But mathematics to Kirby is their journey, their imaginative adventure, and that is why they can finally be happy. Negative 1 multiplied by itself twice is a 360-degree rotation, so that negative 1 is the 180-degree rotation. In that same way, in the final turn of their journey, Kirby found that the imaginary multiplied by itself twice is negative 1, the 180-degree rotation, so that the imaginary is the 90-degree rotation located in the imaginary dimension. That is why there are 3 cube roots, one that is a 180-degree rotation, because taking the cube of that rotates it 3 times and returns it to negative 1, and another that is a 60-degree rotation, and another that is a negative 60-degree rotation, because when the cube is taken of those values, they rotate 3 times, returning them to 180 degrees, equal to negative 1. And those arrows, according to Ark's triangle theorem, all have a length of 1, and never change in length and only rotate in direction. They can now explain that that is why the fourth root of negative 1 is a 45 degree, negative 45 degree, 135 degree, negative 135 degree rotation. Because when those values are rotated 4 times their initial degree, the arrow goes back to negative 1. Those roots lie in that exact coordinate, but not in the sense of an xy coordinate plane, but in the sense of an imaginary plane, where a single number is 2-dimensional. Kirby can see it all now. Multiplying an imaginary with an imaginary is not just the act of scaling an arrow. It is the act of scaling the arrow by the 2 lengths given from Ark's triangle theorem, while also adding the 2 initial angles that the arrows face. These are not just visualizations. They turn what Kirby started with their contradiction in their cubic formula, into the most profound proof that an imaginary realm exists, and that every operation made so far in the equations has meaning, that mathematics can sometimes be a beautiful field, but sometimes a useful one as well. Kirby is happy, and they can't even imagine the vast amount of imaginative results that they could potentially find in their imaginary realm that they discovered. But Kirby finally acknowledges their fatigue. They have never used so much imagination in a single day. They are able to control their impulse to dive further, because they want to sleep. So that is what they do. Ryemon and Kirby sit together at lunch. On that special day, Ryemon had promised Kirby that he will cook for them, because he had something to show Kirby. They sit outside at a bench, and Ryemon opens his notebook. He shows to Kirby the complex plane, with a grid of lines that only start when the real part is greater than 1. Ryemon then flips the page, and Kirby sees what they perceive as a transformation of every point in that grid. As you know, I've been looking into imaginary functions lately, Ryemon started. Yesterday, I was looking into the zeta function, which is the transformation you see there. I start with the imaginary plane, I take the entire highlighted grid as the input, and every number moves to another. Or in this case, every line of the grid transforms into where each point of that line is outputted to, creating this beautiful pattern. Kirby agrees it is an elegant transformation. Ryemon is a bright mathematician, and he is excited to share his results. But as you can see here, Ryemon says, I only took the transformation for numbers with a real part greater than 1. And that's because I couldn't. At least not without imagining that I could. The definition of this function is the sum of the series of terms, 1 over every positive number, to the xth power. If I plug in a number with a real part less than 1, this sum doesn't converge to a finite number like all of the other sums. It splits to infinity. And that is where I had the idea to imagine that this sum doesn't actually split to infinity. Riemann flips to the next page, and Kirby's hyper-focused eyes follow. I noticed that the arcs created by the transformation are so elegant, but that the arc stops so suddenly in the right half of the plane that it would be completely believable to extend them to the left plane in a unique way. And I found that unique way. The unique way is to preserve the angles. You see how we begin with just right angles? When we take the transformation, those same right angles are preserved. Every intersection you can make is preserved. In other words, I just need to imagine that this transformation continues. Even if the number splits to infinity, I can converge them back by drawing in the only unique way that the angles are still preserved. Riemann glances at Kirby. They expect to see their final result from this so-called imaginative continuation. Riemann flips to the final page. I think these ideas are beautiful, Riemann remarks, but I found something even crazier. I saw your result on the infinite sum, 1 plus 2 plus 3 plus 4, and so on and so forth, and how if you imagine a sum to equal some finite value, then it equals -1 over 12. Well, that turns out to be represented in this imaginary transformation too. A number to the negative first power is the reciprocal of that number, but in the case of my zeta function, the number is already in the reciprocal form, so that taking the negative first power just turns every number to the positive numbers. So, zeta of -1, according to your proof, Kirby, is equal to -1 over 12. And according to my imaginary continuation of the imaginary transformation, it is also equal to -1 over 12. This is what I wanted to share with you, Kirby. What do you think? Kirby and Riemann continue their journey into mathematics, finding beautiful explanations, failing to find beautiful explanations, imagining boundaries outside conventional knowledge, and being alive. Sometimes a part of their insight takes the lead, and other times another part finds an imaginative idea that applies to find a simple, elegant solution. In unfortunate times, Kirby dislikes a part of themselves, and as Kirby understands it, that is completely valid. They acknowledge their emotion, cry out, and they feel better. They know that it's going to get better someday, that their inner imaginations can someday love and understand each other, converging to a united and forward-facing whole, one.